In this video, we are going to look at implementing a simple AXI peripheral to implement a performance counter. A performance counter can be used inside a C program written in the SDK to estimate the number of clock cycles taken by a function to execute, or in general to time any event that is happening on the FPGA in terms of number of system clock cycles. We will first implement this performance counter using Vivado HLS. Implement an AXI Lite interface that will allow us to read out snapshots of the counter into the microblaze or any other AXI Lite compatible processor. In our example, of course, we will use the microblaze. And finally, we will show some example code that can be used to profile the time taken by functions to execute. The assumption over here is that you have already completed some of the previous videos in this series. In particular, you are familiar with how to implement the Vivado HLS design for a 32-point FFT, including packaging and export of the IP core. Also, you have completed the Hello World example on an FPGA board. The example demo given in the video is for the Basis 3 board. If you have another board, you will need to modify it appropriately. We will begin by creating the performance counter IP using Vivado HLS. I have already created these projects, therefore I am only going to show you the final result. The source code for the individual files is available on the GitLab project and you are welcome to use it. But the details of how to create the project, implement it, export the IP, etc. will not be looked at in too much detail over here. So as you can see here, the source code for the performance counter is almost trivial. It just consists of a simple function which returns an integer. It does not take any inputs. I have declared a static variable called counter and initialized it to 0. A static variable is one which retains its value across successive invocations to a function. Now, in terms of hardware, what that means is it will create a register that will hold a value across successive invocations of the module. Each time what happens is that counter will be incremented by 1. So in other words, the static int counter equal to 0, the initialization happens only once, and on each successive starting of the module, the counter will be made counter equal to counter plus 1. At any time, if I ask for the return value of this function, it will return the value of the counter. Now you will notice that in the directives tab over here, I selected the value counter and inserted the directive which you can see over here, which basically shows up as #pragma HLS interface s_AXI Lite port equal to return. In other words, what it's saying is that the return value of this function has been defined to be of type s_AXI Lite. This allows us to do two things. One is that the function can now be, the module can now be started from software, and the second is that the return value can be read back using software from the microblaze processor. We synthesize this. You can see that the latency as well as the interval turn out to be 0, which basically means that this effectively ends up being almost like a combinational unit. But on the other hand, it does use a certain number of flip-flops and lookup tables. Those are used for the AXI Lite interface, which is used in order to return the value of the counter, and also of course to keep the value of the counter itself. In terms of the control signals for this, you can see that almost all of them correspond to the s_AXI Lite S port, which has a number of different signals out here, all of which correspond to the AXI bus standard. It also has a clock, an active low reset, and an interrupt output, which we will not be using in this particular design. You will also notice that I did not have a test bench. This design is so simple that I could go ahead and synthesize it without bothering about a test bench. But in general, of course, even for relatively simple designs, you should try and create some kind of a test bench just to confirm that the functionality is as expected. I can then export the RTL. I just leave all the defaults for the settings. And once the RTL export has completed, I can exit Vivado HLS and import this IP into a Vivado project. The Vivado project that I am going to use for importing the counter IP is going to be the same as the one that we use for the Hello World project. But in order to import this new IP, I first need to make sure that my IP settings are correct. I open the settings under project manager, go to IP, repository, and I can add a repository over here. The repository that I would like to add is the one corresponding to counter, which is where I had created the Vivado HLS project. And when I select this, it identifies that one repository was present in this directory and adds it to the project. When I now go to the block design and add IP, I can search for counter, and it gives me the option for performance counter, which was the name that I had given while exporting the project. I can run connection automation and select the AXI light bus, click OK. You may notice that the AXI peripheral interconnect, this block out here, now has two output ports, two M ports, that is master ports. One of them is connected to the UART, the other one is connected to my counter module. Once again, regenerate the layout so that it's all laid out neatly. Validate the design and save it. None of the input or output ports of this design have changed, so I can skip through the process of I/O planning and go straight to the final step, which is generating the bit stream. Once the bitstream generation has been successfully completed, as before, we need to export the design and create an SDK project. Note that when we export this design, since we have modified the hardware, it will create a new hardware definition file, and therefore the SDK might have issues in terms of how it opens up the new project. The question that you can see here is an exported file for this module was found at this location. Do you want to overwrite it? The reason it asks this is because we have now created a new hardware definition file that includes the counter. In this case, of course, we do want to overwrite it, so go ahead and say yes. Launch the SDK. Since we are trying to evaluate the counter project, we actually need to create a new BSP as well as new source code. So what I'm going to do is go ahead and close the old projects that we had here. And start a new application project. I'll call this perf counter just to say that it's a test for the performance counter. Once again, the OS is standalone, hardware platform and processor same as before. In this case, I'm going to select the C++ language. This is because it will help us later when we want to also evaluate the timing required for the FFT module. Start with an empty application, so we can just go ahead and click on finish. When you look at the tab out here, the perf counter underscore BSP shows that under the microblaze 0 tab, you will find in live source there is a counter, and this counter source has a number of files inside it. In particular, we are interested in the file xcounter.h. If we open this file, we will find that there are a number of functions defined in this counter. The ones that we are interested in are counter initialize, counter start, counter enable auto restart, and counter get return. These are the functions that we will be making use of. As you can see, this effectively gives you a nice interface which allows you to start the counter as well as check the done, idle or ready signals. If you recall what the handshaking protocol used for a regular peripheral is, you would remember that it takes a start signal as an input and gives out done, idle and ready as outputs. Now, since we are using an AXI Lite interface, all those signals are being implemented in such a way that they can be read and controlled from software. So how do we make use of this? Let's go and open the perf counter source. In order to make use of the xcounter peripheral, we need to use the API or the application programming interface that is provided in the xcounter.h file. First, we will need to declare a variable of type xcounter, which is this struct that is defined in the file, and then use the functions initialize, enable auto restart, start and get return in order to actually access the counter variables. In order to do this, I have replaced the empty main.cc file which is created when we start the project with the file that has been provided as part of the GitLab code. What you can see over here is the first step that needs to be done is to declare the X counter variable, and then I take XCPTR as just a pointer to that same variable. This is purely for convenience. You could also have replaced this XCPTR with ampersand XC throughout the rest of the code and it would still work. First we need to initialize the code, enable auto restart, and then start the counter. If you go back and look at how the counter was defined, it essentially had just a static variable int counter defined inside it, which means that every time the module is started, the counter would increment by 1. By enabling auto restart, what we are doing is that the counter effectively implicitly increments by 1, and on the very next clock cycle once again receives a start signal, which means that on the next clock cycle it once again increments by 1. In other words, we have converted it into a continuously running counter by enabling auto restart. Further down in the code, we see that we are declaring 3 variables, T1, T2 and T3. The very first function that we call is xCounterGetReturn and take that value and store it into T1. So T1, in other words, will contain the number of clock cycles that have passed since the xCounterStart function was called. T2 will therefore return the number of clock cycles that have passed since xCounterStart, which means that the time from xCounterStart up to the calculation of T1, and then from T1 up to T2. After that, I have 2 printf statements where I print out the value of T1 and then of T2, and once again take the next xCounter value and store it into T3 and finally print that out. In order to capture the output of this, once again we will need to run minicom. As you can see, I have run it with this same settings, 9600 bits per second, 8N1, and connected to TTY USB 1. You will need to adjust this for your hardware. To run the program, we'll go to the run configurations, select all the options as before. Debug type is standalone application debug, connection local. The bitstream file remains the same, mbwrapper.bit. Of course, it is now changed to include the counter. The application, we need to make sure that the project name is now selected as perf counter and not hello. As long as all of that is done, we are good to go, and we can straight away go and click on the run option over here. It takes a little while. You can see some of the messages coming down here, launching GDB, and once everything is reset and disconnected, when we go back to the terminal, you will find that there are a few strings printed out on the screen. The first is of course hello world, and then T1 is equal to 32, T2 is equal to 63, and T3 is a large number, around 1.5 million or so. Let's interpret these numbers. Effectively, in terms of the code, what T1 is telling you is this is the number of cycles between xCounterStart and the first xCounterGetReturn. In other words, effectively it looks as though this is the time required for one single function call to happen. What does that mean? The Microblaze processor itself is working at 100 MHz and the counter is also running at 100 MHz. Effectively, what this says is that there are a few instructions being executed on the Microblaze which end up taking roughly around 32 clock cycles before the T1 value can be captured. This includes the time required for retrieving the data using the AXI Lite bus back into the Microblaze. The next function call is immediately after that, so T2 is at 63 cycles. So in other words, between T1 and T2 we have around 31 cycles, which gives us some confidence that around 31 or 32 cycles is roughly the time required for each function call. T3 on the other hand is a totally different number, 1.5 million clock cycles. If we go back and look at the code, we find that there are 2 XIL printf statements in between T2 and T3. And this clearly shows us that the printf statement, which of course includes sending data out over the serial port, is a very time consuming process. It takes a very large number of clock cycles. Each one of these printfs takes on the order of around 600 to 700,000 clock cycles. So in this way, we were able to construct a basic counter peripheral, give it an AXI Lite interface, attach it to our Microblaze processor, and write a simple SDK code that allows us to read the value back into the Microblaze and thereby find out the number of clock cycles between successive invocations of the getReturn function. When we For example, if we look at the gap between T2 and T3, it effectively tells us that the time required for 2 printf statements is around 1.5 million clock cycles. We could do something similar, for example, to put it around, let's say, the FFT function call and find out the number of clock cycles required in order to compute an FFT. This allows us to do something called profiling, which is basically computing the number of clock cycles or amount of time required for each function, finding out where the bottlenecks are and which ones would benefit from being accelerated in hardware.